We're going to look at the maximum power transfer theorem. This theorem examines how power is transferred from some sort of source into a load. So here we see a voltage source with a Theveninized input impedance and some sort of load. So the question is, what's the maximum power that we can get into this load from this source? And in our case, we're going to assume that the voltage source is fixed, as is the source impedance. So the only variable we're going to look at is the load. Now the power in the load is simply equal to the current times the voltage. So if we were to take a look at the case where the load here is 0 ohms, that would be a short circuit, we would have a massive amount of current flowing in this loop. But because the voltage across the short circuit is equal to 0, this is 0, then the power in the load is equal to 0. So notice here we have load resistance. If the load resistance is 0, the power in the load is 0. Now that's not to say that there isn't real power flowing somewhere, because there is. If this is a battery and we've short-circuited, then there's a massive current flowing in the battery, and it is being dissipated, the power is being dissipated as heat through the internal source impedance. So here we can see why we should never short-circuit a battery, because even though we're getting no power out of it, we're dissipating a tremendous amount of power inside of it. That power manifests itself as heat, and in extreme cases it can even cause a battery to explode. Now, as we change the load resistance from 0 to some higher number, we discover that the current begins falling off, obviously. And if we go to the very extreme and make this load resistance an infinite ohms, we discover something else that's interesting, and that is that the current goes to 0. Well, going back to the expression for power, if the current goes to 0, then the power goes to 0. And so if we go back to our little power in the load curve, when the load goes to infinity, the power goes to 0. So this helps us to appreciate that between these two extremes of a short circuit and an open circuit, as we change the value of the load, the power in the load will rise up to some sort of maximum, and then it'll gradually taper off to 0 again. And so the question we're asking ourselves is, what is this maximum power here in the load, and what should the load resistance be to get that maximum power? To do that, we're going to simply apply this power equation again, specifically for the load, where both the source impedance and the source voltage are fixed. So the current in the load is simply going to equal whatever the voltage source is divided by the total resistance in the circuit. And the voltage across the load is simply the voltage divider rule. It will be the voltage inside the power source divided by times RL divided by RS plus RL. Just the voltage divider rule. And therefore the power in the load is the product of these two. And of course, if we multiply it out, we'll get voltage squared times RL divided by RS plus RL, the quantity squared. So what can we do with this? Well, if we go back to this shape of the curve over here, we notice that the power maximum occurs here where the slope of the curve, the slope of the power curve is equal to 0. So the slope equals 0. And in mathematical terms, that means that the derivative is equal to 0. And it's a derivative with respect to what? Well, it's a derivative with respect to RL, because it's the only thing we're going to change. So that means that the derivative of the function with respect to RL is equal to 0. Now this expression is a little bit complicated to analyze because we've got RL in the numerator and RL in the denominator. So we're going to try and simplify this a bit. So we'll just do that. So we have v squared RL divided by, we'll expand this, RS squared plus 2RL SRL plus RL squared. And again, it's still complicated because we have RL, which is the variable, in the numerator and the denominator. We'd like it to be one place or the other, but not both. So let's divide through by RL, v squared over RS squared divided by RL plus 2RS. RL divided by RL is simply 2RS. And RL squared divided by RL is simply RL. And again, we have the same problem again. We have an RL in the denominator, 1 in the numerator. So we'd like to tidy that up a bit more. So we'll do it one more time. Power in the load is equal to v squared divided by RS squared RL to the power of minus 1 plus 2RS plus RL. Now, we're looking for maximum power. For this power to be maximum, this denominator over here must be a minimum. So what we're going to do is we're going to take the first derivative of this and set it equal to 0. Because the minimum value is the opposite shape of this. At the minimum value, the first derivative is also 0. So that's what we're going to do. We're going to take the derivative of this denominator with respect to RL and set equal to 0. So let's do that. The derivative of this expression with respect to RL, so it's RS squared RL to the minus 1 plus 2RS RL plus RL, oops, not RL here, it's gone, plus RL, there we go. Take the derivative of this, and what do we get? Well, the derivative of RL to the minus 1 is minus RL to the power of minus 2. This RS, of course, is simply a constant, so we're going to end with minus RS squared RL to the power of minus 2 plus 2RS is a constant, so the derivative of that is equal to 0. And the derivative of RL is simply 1. And what are we going to do? Well, we're going to set all of this equal to 0. So now we can move 1 over to the other side. So we're going to rearrange this expression slightly. And we're going to get RS squared over RL squared is equal to 1. So from this, we can clearly see that RS squared is equal to RL squared. And from this expression, we can clearly see that RL is equal to RS. So this is what we're looking for. In this curve over here, this maximum occurs when RL is equal to RS. When this impedance, the load impedance, is equal to the source impedance. And this is called a matched load. And so the question now is, what is the power in the load under matched conditions? Well, to discover that, we're simply going to have to calculate the power, which we've already done. It's right here. And in this expression, we're going to put in the value of RL every time we see RS. And so that'll give us a maximum power here. So power in the load maximum is equal to V squared RL divided by RL plus RL squared. And from here we can see that this is simply equal to V squared RL over 4RL squared. And of course, then RL cancels. So the net result is the maximum power on the load, PL max, is equal to V squared over 4RL. This represents the maximum amount of power that we can extract from a power source under matched conditions. And this is the crucial thing to remember, is that we're talking about having this value fixed. Now, let's say this value was not fixed and we're looking at something else. How could we increase the power in this if they were, let's say, matched? Well, one way you could increase it is by lowering this, RS. Well, now they would no longer be matched. The power in here would go up. But to increase the power even further, we would lower this to match that. And we would still end up at the maximum power conditions. So this is a crucial thing to remember about the maximum power theorem, is that it's working on the assumption that the source impedance is fixed. Now, this could be a battery, this could be a hydroelectric power plant, any kind of power source like that. But it could also be a signal generator or a function generator. And so you'll notice that in many function generators or signal generators, they specify right on the front panel the source impedance. And the reason why that's there is so that you know that you'll get maximum power out when your transmission line, your load, is equal to that source. Now, if it's not, you will not get the maximum power out. And furthermore, an interesting phenomenon happens that if you put in a signal out into the load and it's not matched, part of that power will be reflected back into this source. And that can cause problems in the transmission lines. So hence, when we start looking at transmission lines, we'll discover that it's very important to match the transmission line to the source impedance of the signal.